In this video, we're going to be looking at work done in motion graphs, and this is video 3 of 6 for our forces topic. Let's get right into it. So, work done in energy transfer. You should remember that work done means energy transfer from the energy topic. When a force does work on something, it transfers energy. So when a force causes displacement of an object, work is done and energy is transferred. A lot of the time, the energy transfers into heat as there is friction. Work done is energy transferred, so its unit is the joule, and joules are given the symbol J. Let's have a look at our next formula now. Work done is equal to force times distance, where work done is measured in joules, force is measured in newtons, and distance is measured in meters. Now, for this formula, distance is the distance moved along the line of action of the force. That just means the distance moved because of the force directly. So let's have a look at a worked example. How much energy has to be transferred when a car moves with a force of 800 newtons over 2 meters? Well, let's write down our equation. Work done is force times distance. So 800 is our force and our distance is 2 meters. So our work done is 800 multiplied by 2, which is 1,600. The units of work done are joules, as it is a measurement of energy. So our final answer is 1,600 joules. How much energy does a dog need to jump 10 meters if he has a mass of 20 kilograms? Well, let's write down our equation. Work done is force times distance. Now, we need a force and a distance here. We'll have a distance of 10 meters, but we need to find the force. Remember, weight is equal to mass times gravity, so we can work out the weight or the force. Weight, which is the force, is equal to mass times gravity. Our mass is 20 kilograms and gravity on Earth is 9.8. That means the weight or the force in this question is 196 newtons. Write out our equation again. Work done is force times distance. Well, that's just 196 multiplied by 10. Meaning our work done is 1,960. Work done is measured in joules, so our final answer is 1,960 joules. It's really important that you know about units. 1 joule of energy is exactly the same as 1 newton of force travelling 1 metre. So 1 newton metre is just the same as 1 joule. So when this man pushes this box along the ground, he is doing work against the force of friction. Energy transfers into thermal energy in the box, making it heat up. It also produces sound energy. So when this man does work against the force of friction, he's converting energy, he's doing work, which is just the change of energy from one form into another. He's converting his kinetic energy of that box into heat and sound energy as it moves along the floor. Work done is just the amount of energy transferred. Since energy is measured in joules, work done is also measured in joules. Friction always acts against objects when they are touching and rubbing off of each other. Friction is a resistive force. It acts to oppose the primary force. Doing work against friction causes heat to build up. You get an energy transfer into heat whilst you are doing work against friction. So if you take your hand and rub it over the carpet, you will find that the carpet gives your hand some resistance, and that force that the carpet is giving your hand, well, that's friction. So when you rub your hand over that carpet, you have to put energy into rubbing your hand across the carpet, and you're doing work because you're converting the energy which is in the kinetic store in your hand into heat energy and sound energy as it goes over the floor. If you're following along in your revision workbook, pause the video now and complete task number 10. So next we're going to have a little look at speed. Speed does not include direction. It is a scalar quantity. This means I could be travelling 3 meters per second, but in any direction. So what actually is speed? Well, speed is the amount of displacement per unit time. If I am travelling at 3 meters per second, it means that in 1 second I have moved 3 meters, because you're travelling at 3 meters per second. If I'm travelling at 20 miles per hour, it means that in 1 hour I will travel 20 miles. So if you're moving at 20 miles per hour, after 1 hour, you will have moved 20 miles because you're travelling at 20 miles per hour. Speed is rarely constant. Mostly when people walk and cycle, their speed changes. When people travel in the car, their speed also changes quite a lot. The speed at which a person can walk, run, or cycle depends on many factors, including age, terrain, which is just the shape of the land, fitness, and distance travelled. Age makes a difference because the older you are, the harder you find it to walk faster. Terrain makes a difference because you tend to go slower up hills. Fitness makes a difference because the fitter you are, the easier you find it to travel faster. And the distance you've already travelled also makes a difference. If you've travelled far already, you may be feeling tired. So all of these factors change your speed while you're walking or cycling. You need to know these typical values for speed. So the typical value for the speed which someone walks is 1.5 meters per second. The typical value for speed that someone runs is 3 meters per second. The typical speed of someone who is cycling, well, that's 6 meters per second. And if you're travelling by car, then the typical speed for that will be 13 meters per second. So what else has speed variations? It is not only moving objects which have speed. The wind has speed, and it varies constantly. Sound also has speed, and that varies as well. So what is the speed of sound in air? Well, the speed of sound in air is 330 meters per second. That means in 1 second, sound can travel 330 meters. But that isn't as fast as the speed of light, which is about 300 million meters per second. So that is outrageously fast. One of the most famous equations in physics is next. There is a very famous equation relating speed, distance and time. Do you know this equation? You probably do. Speed is equal to distance divided by time. Speed is distance over time. So rearranging that formula, we get our next equation. And that is distance travelled is equal to speed times time. S is equal to Vt. So let's have a look at how this is used. In physics, V means speed and S means distance. So that's quite confusing because you would think that S would mean speed, but no, V is speed because velocity is related to speed and V is the first letter for velocity, and S, well, that's distance in physics for some reason. So distance travelled, S, speed, V, time, T. Let's have a look at a work example. A car travelling 9 meters per second travels along a straight stretch of road. How far will the car have travelled after 2 minutes? Well, firstly, we need to convert our units. So we'll have in the question 2 minutes. Well, 2 minutes, that's 120 seconds. S is equal to Vt. So our distance travelled is equal to 9, because that's the speed, 9 meters per second, multiplied by 120, because that's our time. So our distance travelled is 1080. Distance is measured in meters, so my final answer is 1080 meters. What is the speed of a hamster if it ran 5 meters in 8 seconds? Well, firstly we're going to write out our equation. Distance equals speed times time. Rearranging this formula to get V on its own, well, that's the same as speed is equal to distance divided by time. That's the more famous form of this equation. So the speed that the hamster runs, well, that's 5 because it ran 5 meters, divided by 8 because it took 8 seconds. So the speed of the hamster is 0.625. Speed is measured in meters per second, so my final answer is 0.625 meters per second. Can you calculate the speed of something at a constant speed? To measure the speed of something, you will need to take measurements of time and distance. To do this, simply measure the distance travelled with a meter rule or a tape measure. Use a stopwatch to record the amount of time it takes to complete the said distance. Now use V equals S divided by T to work out the speed of an object. Let's do a little experiment. So, using a toy car and a stopwatch, we're going to calculate the speed of the toy car. So, in 3 seconds, that car travelled 60 centimetres. So can you work out the speed and remember to convert your units? Well, let's have a look. 3 seconds, 60 centimetres, that's 0.6 metres. So if it travelled 0.6 metres in 3 seconds, that means it travelled 20 centimetres in 1 second, or 20 centimetres per second. But 20 centimetres is the same as 0.2 metres. So in standard units, that car travelled 0.2 metres per second. Objects often speed up and slow down, so finding an exact speed can be tricky. Average speed can be used to work out an average for non-uniform motion, i.e. the speed changes. You can use the total distance and the total time taken. So let's have a look at a worked example now. A train, not travelling at a constant speed, travels from Newcastle to Durham. It took a total of 12 minutes and it is a distance of 16 miles. Calculate the average speed in miles per hour. So obviously, because the train didn't travel at a constant speed, some of the time the train was going slow and some of the time the train was going a bit faster. But we're going to work out the average speed. Okay, so the average speed is the total amount of time and the total amount of distance, and you plug those into the equation. So let's write out our equation first of all. Distance is equal to speed times time. Rearranging that, speed is equal to distance over time. So we're going to convert minutes into hours. So 12 divided by 60 is 0.2. V is equal to 16 divided by 0.2. So our velocity, or our speed, is equal to 16 miles divided by 0.2 hours. So that means our speed is 80. In this question, the units are miles per hour, so my final average speed is 80 miles per hour. If you're following along in your revision workbook, pause the video now and complete task number 11. Okay, next we're going to have a look at velocity. The velocity of an object is its speed in a given direction. Velocity is a vector quantity. Velocity could be 30 meters per second northeast, whereas speed would just be 30 meters per second. So velocity includes a direction, as it's a vector. The length of this road is 750 meters. The distance travelled, therefore, is 750 meters. So if you have this car travelling along this road, where upwards is north, the car might only go from this point here to this point here. But the journey that that car has taken is a little bit longer than that. So, if that road is 750 metres long, it means the car has travelled 750 metres. But the displacement of that car is much less than 750 metres, because if you draw a straight line from the start to the end, it's only 600 metres. If the time taken was 60 seconds, then the average speed would be 750 divided by 60, which would be 12.5 metres per second. And that's because you've taken the distance travelled, and you've taken the time, and you've inserted it into the formula to get your speed. But the velocity would be 600 divided by 60, and that's because the velocity has a particular direction, and in this case it is this direction, or southeast. So, taking the values from the displacement and the time and plugging it into the equation, well, 600 divided by 60, that's 10. So the velocity of this car is 10 meters per second southeast. Acceleration is defined as the change in velocity. How might an object travelling at a constant speed be accelerating? Because the velocity is changing. It's changing direction. This is also true for planets in orbit. The Earth is travelling at a constant speed around the Sun, but because we're changing direction constantly, because we're travelling in a circle, the Earth is constantly accelerating but not changing speed. It really is quite hard to get your head round. Something can be accelerating without changing speed because the velocity is changing. But how is the velocity changing? Well, the velocity is changing because the direction is changing, and velocity depends on direction. So even if something's travelling the same speed, if it's changing direction, the velocity is also changing. If you're following along in your revision workbook, pause the video now and complete task number 12. Moving on. We're going to have a look at distance time graphs now. For objects moving in a straight line, you can use a distance time graph to model the speed and the distance travelled at a particular moment in time. Distance time graphs have time on the x-axis and distance on the y-axis. And they look a little bit like this. Distance on the y-axis, time on the x. The distance increases at a constant rate for objects travelling at a constant speed. And this makes sense. If something's travelling at a constant speed, it's going to gain distance at the same rate over the same amount of time. So let's draw a line to illustrate that. Here we'll have something travelling at a constant speed. As I say, it makes sense because they're moving away from you, and as time goes on, the distance from you increases. Objects which are stationary have flat lines. This also makes sense. If an object is staying still, then it is not gaining or losing distance from you, so the distance stays the same. Objects which are accelerating have curved lines. If the curve is going upwards, it's getting faster, downwards, and it is decelerating or getting slower. This makes sense. If the speed is gradually getting faster, then its rate of change of distance will increase. As it gets faster, more distance will be covered. A runner runs 30 metres. They then turn around and run back. Let's sketch a distance time graph for this runner. Well, this one's quite easy. Over time, the distance which the runner is away from the starting point gets bigger. And then, once the runner has ran 30 metres, they then come back and the distance they are from the starting point gets smaller, it reduces. And then, after a certain amount of time, they are back at zero distance. They are back to where they started. Drawing detailed distance time graphs. When you are drawing detailed distance time graphs, you have to have a scale. There is a scale, normally in seconds, along the x-axis, and a scale, normally in meters, along the y-axis. If you know the details of a motion, then you can create a distance time graph. Let's look at an example. A car travels 300 meters in 20 seconds. It then comes to a stop for 10 seconds before traveling 100 meters in 10 seconds. Draw a distance time graph for this. So, first, we'll need to come up with a scale. The whole motion is 40 seconds. So along our x-axis, we're going to draw the scale, and we know the whole motion is 40 seconds because you can add up all of the times. So that means at the extreme, we'll have 40 seconds, and then at equal intervals, we'll have our tens, so 10, 20, 30, 40, and obviously time is measured in seconds. Next, we're going to come up with a scale for our distance, and again, we're going to make intervals of equal distance between them, with 400 being at the extreme because the total distance is 400 meters. Now, we're going to draw in the lines. So, as the question states, the car travels 300 meters in 20 seconds. So, in 20 seconds, and in 300, or after a distance of 300 meters, we can put a point here and then draw in our line. The car then stops for 10 seconds, so from 20 to 30 seconds, the distance does not increase when the car stopped. And then it travels 100 meters in 10 seconds. So we can say it goes from 300 meters up to 400 metres, well that's a distance of 100 metres, and it does it in 10 seconds. A reminder of what's what in a distance time graph. When you have a straight line, you have a steady speed. When you have a flat line, you have something which is stationary or not moving. And when you have a line which is going back towards the 0 point, you see that the object is returning to the start, or it's coming back. If you have a line which is curved like this, it's accelerating, or if the curve is like this, so sort of curved the other way, then it is decelerating. What's happening in this graph? Well, you can see that at 0, the distance is 3 metres. So when we have started, let's say, the stopwatch, the mouse is 3 metres away. Then, between 0 and 5 seconds, the mouse is running away from us, because you can see that the distance is getting bigger. The distance is growing between us and the mouse. Then, between 5 and 15 seconds, so for a 10-second period, the mouse is staying still, because the distance isn't changing between us and the mouse. Then at 15 seconds, well, here you can see a line returning to the 0 point, so that means the mouse is coming towards us. And then at 30 seconds, the distance between us and the mouse is 0, so the mouse is right next to it. So in this distance time graph, we'll have a constant speed here. So A is a constant speed, so the first 5 seconds this object is travelling at a constant speed, quite a quick speed because it's going 15 metres in only 5 seconds. Then the object travels at a smaller speed, between 5 and 15 seconds, it travels 5 metres. And then between 15 and 20 seconds, the object is stationary because the distance isn't gaining or reducing from where we are. Then, after 20 seconds, the line returns towards the 0 point. It is going downwards like that, and that means the object is returning to where it started from at quite a big speed because it's quite steep. So you can work out the speed of an object by using the gradient. The gradient of the graph shows you the speed of the object. This is because speed is equal to distance divided by time, and the gradient is change in x divided by the gradient is change in y divided by change in x. And for a distance time graph, this is just the same as the change in distance, because distance is on the y-axis, divided by the change in time, because time is on the x-axis. So using the gradient, we can find the speed. Let's work out the speed of the car in the first 20 seconds. Let's use the gradient. Draw a line going along and up like this. Now measure them and work out the change in time and the change in distance. So the question asks about the first 20 seconds. So we're going to draw a line from 0 to 20 seconds. Well, that means that line is 20 seconds long. And we're going to go from 0 up to 300 metres. And that means this line is 300 metres long. Once you have these values, use the gradient equation, change in y divided by change in x, to try to work out the speed. So speed is change in y divided by change in x. Well, we know the change in y is 300 and the change in x is 20. So 300 divided by 20, well, that's 15. And the unit for speed is metres per second. So using the gradient from that graph, we found that the speed of this object is 15 metres per second between 0 and 20 seconds. So what if the object is accelerating? Well, if the object is accelerating, then we use a tangent. Remember, acceleration on a distance time graph is represented by a curve. A tangent is a straight line which is drawn on a curve. It only touches the curve once and gives us an idea of the gradient at that particular point. So, what is the speed of this object at time t equals 85? Well, 85, that's somewhere around here. So we're going to draw on our tangent at this point. So the tangent only touches the curve at 85 seconds. Next, we're going to calculate the gradient, and to do that, we're going to draw in our little triangle and measure the length of each of the sides. So the change in y is 16 metres, and the change in x is 40 seconds. So what is the speed? Well, remember, to calculate the speed from a distance time graph, you just look at the gradient. And the calculation to work out the gradient is the change in y divided by the change in x. So for this graph, we'll have 16 divided by 40. So at time 85 seconds, our speed is 0.4 meters per second. And that's because 16 divided by 40 is 0.4, and the unit for speed is meters per second. If you're following along in your revision workbook, stop the video now and complete task number 13, and note that for this task there is more than one page of work.
Thank you very much for watching. Workbooks and test papers which integrate with these videos and online courses are available at our website, backrowtutoring.com.